Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Assalamu alaikum to everyone. Today we are going to start a very exciting and interesting topic, particularly for the foundation design, and probably the most difficult of the problems that a geotechnical engineer is asked to solve is predicting or estimating the settlement of the loaded foundation. Now, why it is difficult, a challenging problem. So we discussed briefly in Geotech 2 that the total settlement is important, but also the rate of the settlement is also important. And then we also discussed that there are different components of the settlement which is occurring beneath the foundation in the soil, such as the elastic settlement and consolidation settlement, which is also known as the primary compression and the secondary compression as well. So the contents of our today's lecture would be discussing the foundation settlement, introducing the concepts of the settlement, some typical loads on the building foundations, number and depth of the boring, why we need to find out the why we conduct boring into the soil. So we usually collect samples and we investigate the soil properties. Then the immediate settlement calculations using theory of elasticity will be explained, and standard penetration test procedure would also be explained, which you might have performed in Geotech 2 lab. Standard penetration test corrections, different corrections which are applied to the SPT N value will also be discussed in today's lecture. SPT correlations, when we get the SPT N value, we correlate that with different properties of the soil so that we can obtain those properties. As a geotechnical engineer, we need those parameters, those properties to find out the settlement of the soil. Now, immediate settlement using the standard penetration test will also be discussed at the end of today's lecture. So starting with the foundation settlement, as you remember from our earlier lecture, that there are two foundation design criteria. One is the shear failure criterion, and another one is the settlement criterion. So chapter 2 was related to the shear failure criteria, in which we discussed that how we can find out the bearing capacity of the soils. Now chapter 3 would be dealing with the settlement criteria. Sorry, that's chapter 3. So this is the chapter number 2, which we discussed. This is the base shear resistance or the shear failure criteria. Now the settlement criteria would be discussed in chapter 3 here. Now, why the information, or why we estimate the settlement? Because excessive settlement can cause structural damages to the buildings, nuisances such as sticking doors to the windows and cracks in the tile and plaster, excessive wear or the equipment failure from the misalignment resulting from the foundation settlements if we are dealing with the machine foundations. So these problems and nuisances can create significant economic losses as well. So therefore, it's important to estimate the accurate foundation settlement. But you need to note down that the settlements are only the best estimates. So we try to accurately estimate those foundation settlements, but it's unfortunately we are unable to get the desired value. For example, if we compute the settlement of the foundation, which is equal to 10 millimeter, now it's okay if you are not measuring, more accurately. So if the real settlement is occurring, for example, 5 millimeter or 20 millimeter, so the foundation can handle those variations or those differences which are occurring in the estimate and in the reality. What we usually don't want in the settlement estimation, that for example, if we estimate the foundation settlement 25 millimeter and in reality the settlement would occur 100 millimeters, so that would be significant variation and difference in the results. So therefore we try to get the best estimates of those settlements in order to avoid all these problems which we discussed in here. Now there are two major problems in estimating the settlement, and those are due to the estimation or obtaining the reliable elastic parameters, which are the E and the Poisson ratio. Another problem in estimating the settlement would be obtaining the reliable stress profile from the applied load. So the stress profile beneath the foundation that also cause the variation or variability in estimating the settlement of the foundations. Now we will refresh your concepts and ideas which we discussed a little bit in Geotech 2. So regarding the components of the foundation settlements, so if you remember, immediate settlement is one part of the total foundation settlement. Another one is the consolidation settlement, and the third one is the secondary compression or secondary settlement. So delta HI is the immediate settlement, delta HC is the consolidation settlement, delta HS is the settlement which is occurring due to the creep or the time dependent and particle reorientation is occurring in organic soil. So the immediate settlement is particularly dominant in sands and gravels. Consolidation settlement is particularly dominant in saturated clays, and secondary settlement is predominant in organic soils. And if you remember, we discussed that these immediate settlement usually occurs due to the expulsion of air or gases, or the particle, a little bit of the rearrangement as well, because the immediate settlement, these are recoverable deformations. So if the load is applied on top of, if it's not that much huge, and if the load is applied onto the soil, for example, if the load is applied onto the soil and if that load is not huge, now if this settlement, this immediate settlement is occurring, and if this load is removed, now it will recover again to its original position, because that is dependent upon the modulus of elasticity of this particular soil. And the delta HC, which is the consolidation settlement, and we discussed that this is happening due to the dissipation of excess pore water pressure, and it is also time dependent. So that is due to the dissipation of the excess pore water pressure. Secondary compression is a complex behavior, and it's not well known, but it is attributed to the particle rearrangement or the plastic deformation which is occurring through many years in those types of soils, such as the organic soils. Now if you see here, the term U is added here with the consolidation settlement, which is the related concept which we understood in Geotech 2, which is the degree of consolidation. For example, if the degree of consolidation is 0 and time is at the start, then the dissipation of excess pore water pressure has not been occurred yet. Therefore, that U is equal to 0. And if T is equal to the TF, so the degree of consolidation would be 100%. And then you can use this equation to find out the total or final settlement. Okay. So terms are given, delta H, you can write that as total settlement, delta HC, consolidation settlement, delta HS, secondary compression, and U is the average degree of consolidation. The discussion which was done in the previous slide is also discussed here in detail, that the immediate settlement usually takes about 5 to 7 days, and it predominates in saturated or unsaturated cohesionless soils that are having high permeability, and unsaturated clays and cells as well. Now, immediate settlement analysis are used for all fine-grained soils if the degree of saturation is less than 90%. Now, for all coarse-grained soils, standard-grained with large coefficient of permeability, so these types of soils also experience immediate settlement. Coming to the consolidation settlement, consolidation settlements are time-dependent, as we discussed, and we have seen that happening in the very famous case study, which is the Leaning Tower of Pisa. We have seen and experienced that over 700 years, the consolidation settlement is occurring, particularly in those types of clays. That settlement is occurring, like huge amount of settlement is occurring there. And consolidation settlements predominates in saturated, nearly saturated fine-grained soils. In consolidation settlement, we are interested both in the consolidation, the magnitude of the consolidation settlement, and the rate at which the consolidation settlement is occurring. Okay. Now, the secondary compression, or you can name it as creep as well, that occurs due to the rearrangement of the clay particles into more stable configuration under constant effective stresses, predominates in highly plastic clays and organic clays. Now, we need to estimate the settlement, and in order to estimate the settlements, we need to collect the samples from the field. So if we are given with a building, we are given with a plaza, we are given with a multi-story building, so these types of structures require different types of borings. For example, if you have a level ground, so it's better to get 3 borings, minimum of 3 borings should be performed. But when the surface is leveled and the first 2 borings indicate the regular stratification, for example, if it's sand and if it's giving us clay, so we don't need to repeat the 3rd borings in order to save some money on the for the projects. Now, 5 borings are generally preferable and recommended at different corners and at the center. For example, if this is a plan of the building, so it's recommended that we, as a geotechnical engineer, perform 4 borings at the corner and 1 at the center to collect those soil samples. Now, if there is a tower or antenna is constructed, so what we can do, we can only perform at that particular location that boring can be performed, or we can perform boring just beside that location as well. Now, the depth of the boring concept is important, and it has been discussed here that for strip footing, we can go for 6.5 B, and there is a reason that for a strip footing, the stress is applied here, and that stress would be higher just beneath the foundation, and as we go along this depth, the stress increase will be equal to the 10%. Okay, that stress, for example, 100 kilopascal is applied on top of this foundation, so that stress increase would be 10 kPa here. Now we need to know the stratification and the soil properties of this particular location beneath the strip foundation. Similarly, if we are given with a square foundation, that case, the 10% of the Q naught, so you can say that this is Q naught, and this stress is applied here, Q naught, this is the net stress which is applied at the foundation level. So the information and the soil properties of this particular depth is important. At least of this depth is of interest for geotechnical engineers. Now for circular footing, you can say 10% of the Q naught will occur at the 2 times the diameter of that circular foundation. Now, these are theoretical values which are given based upon different trial and error. There are other concepts are also discussed, that the footing sizes are seldom known in advance of the borings. So a general rule of thumb is to go 2 into the least lateral dimension of the building. So what does it mean? That, for example, if we are given with a plan view of 100 feet and 30 feet, so what we need to do, we need to do boring till 2 into that least lateral dimension, and the least lateral dimension is 30 feet, so we need to go till 60 feet. But still there is also a problem, because if we are having a 1-story warehouse or a department store, so the loads won't be too much, so therefore it's better to go just 6 to 15 meter deep. That boring should continue till 6 to 15 meter. And for high-rise building, it is recommended that we need to reach to the hard stratum competent soil, or the bedrock should be touched, or we need to get this information from the high-rise or highly loaded foundations. Now coming back to the settlement, there are 2 methods which are used to find out the settlement of the immediate settlement of the foundations. So one method is the theory of elasticity, the another method is the standard penetration test. Please confirm that you can hear me and the screen is visible.
Yes, sir.
Thank you. Okay. Now in immediate settlement, first we will discuss the theory of elasticity. And in theory of elasticity, please kindly note down this important equation, where delta Hi is equal to Q naught B prime 1 minus mu square of mu and divided by Es into M into I. I will explain those parameters one by one. First, Q naught is the intensity of the contact pressure. This is the net pressure intensity at that foundation level. B prime is the least lateral dimension of the contributing base area, and the units should be same as delta H, or the immediate settlement. Es and mu would be the elastic parameters, and M is the number of corners contributing to the settlement. For example, if it is asked in a question that you need to find out this is the foundation and you need to find out the settlement beneath this corner. Now in that case, L prime would be equal to L and B prime would be equal to B. So M would be equal to 1 in this case. Now in another problem, you might be asked to find out the settlement at the side of this foundation. So in that case, we will divide this footing in two parts like this. Now M would be equal to 2 in this case. Now in another problem, you might be asked that you need to find out the settlement at the center or under the center of this footing. So you will divide this footing area into the 4 different parts and M would be equal to 4 because there are 4 corners of these corners which are contributing to the settlement of the foundation. So I hope it's clear. The M concept is important here. Then we will explain the I, shape and rigidity factor, but to explain the shape and rigidity factor, you need to understand the concept of the thickness of the layer, which is of interest and importance in the theory of elasticity. Now, for example, this is the foundation here. This is the width of the foundation, and we are experiencing, based upon the depth of the borings, we find out that this is the height or thickness of the layer. Now, what if that we don't experience the hard stratum here? So it's recommended that we should go till 5B, okay, and B is the width of the foundation. Now we need to take that edge, whichever is minimum of the 5B or the depth to the hard stratum. Now how we can determine the hard stratum? And the hard stratum can be determined based upon the value of modulus of elasticity. For example, if the modulus of elasticity is 10 kilopascal for the layer 1, and we are experiencing another layer here, and the modulus of elasticity of that layer is, for example, 100 megapascal, and this is the 10 megapascal, so it should be 10 times of the modulus of elasticity from the previous layers. Now a weighted average concept can also be used if we don't have a single layer. For example, if we are given with 3 layers, E1, E2 and E3 are given, these 3 layers are given, and the heights are also given. So you can use this equation. Please kindly note down this equation as well, because we are going to use this equation in solving problem in a few minutes. So if we simply multiply the modulus of elasticity with the depth of the layer, and then we multiply the second one, and then we add the third one, and we divide that by the h. For example, this whole z1 plus z2 plus z3 would be equal to the height of those 3 layers. Then we will get the average or the weighted average modulus of elasticity for those particular layers. Now we are here to understand the concept of the shape and understand the concept of the shape and rigidity factor. Now this I, or the shape and rigidity factor, usually which is used in the theory of elasticity, that accounts for the thickness of the soil layer, shape of the foundation, flexibility of the foundation, and the theoretical values we can obtain from this table. Now first we need to find out the h by b prime, and once we get the h by b prime, so you can use this column, and based upon the Poisson ratio which is given 0.5 or 0.33, usually 0.55 is used, 0.50 is used for saturated clays in undrained conditions. In most cases, for sands and clays, 0.33 is used. Now there is another ratio which you need to find out, which is L prime divided by B prime, and L prime and B prime is explained in here, that based upon the location of settlement calculation, you can use L prime and B prime accordingly. Once we got those L prime and B prime value, for example, if the Poisson ratio is 0.33 and you came up with the H by B prime 1.5 and the L prime divided by B prime is 5, so you can go here. 0.25 would be the shape and rigidity factor, but sometimes you will get a value which would be in between these two. For example, .5 and 1.0, there will be a value which would be 0.7. Now we need to find out the shape and rigidity factor somewhere in between, or even we can get L prime divided by B prime, which would be in between here, which is 1.18, which we are going to solve a problem here today as well. So how we are going to get the I value, or the shape and rigidity factor value? So here is a short numerical which is solved here. Please kindly calculate and confirm that those calculations are correct and there are no issues with these calculations. So for example, the foundation is placed in here and the depth of the foundation is 3 meter, and that Q naught, which is the pressure intensity, the net pressure intensity at the foundation level, is 134 kilopascal. The dimensions are given. The width of the foundation is 33.5 meter and 39.5 millimeter is the length of the foundation. Modulus of elasticity for the sandy soil layer is 42.5 megapascal, and for the clay soil layer it is 60 megapascal. Heights are also given. Okay, so you can use simply the weighted average concept and you will find out that the modulus of elasticity is equal to 55 megapascal. Now the height, which is here, this one, so h would be 11 meter and b prime would be simply dividing b divided by 2. So we will find, because assuming that in the example we are asked to find out at the center, the settlement, at the immediate settlement, we need to find out under the center of that footing. Excuse me. Now we will also find out the h by b prime, which is 0.66, which is close to 0.7, and L prime divided by B prime, which would be 1.18. We can assume the Poisson ratio 0.33, and I we can find out using the linear interpolation, which I will explain in a few minutes. So once we get all these values, we can simply plug in those values in this equation. Please kindly note down this equation because it's important from exam point of view, quiz and assignments point of view. And we will come up with the immediate settlement, which would be 0.0175 meter or simply 17.5 millimeter. Now, how we can find out the I factor or the shape and rigidity factor, and how we can use the linear interpolation. So we were given with the x1 value and x2 value and x value. Okay, now we are given with the y1 value, the y2 value, and we need to find out the y value. So if you use this equation and if you simplify that, so I have done it for you, so please kindly give me this value here using the, this is the x1, and we need to find out this y value because the x is given, which is 0.66 or 0.7 if we round off. Please kindly give me the y value.
क्वेश्चन तो दिखा है ना सर.
Please kindly take a screenshot or a picture of this slide, this screen. Because I need to take the attendance as well. 28. $0.13. 0.13. So it's somewhat 0.128, 0.13. And then if you see here, this is for L prime divided by B prime 1. Now you need to do the linear interpolation, and you need to use the same equation for this one as well. And you will linear interpolate here between these two values, and you will come up with a y value here. Then you need to linear interpolate between these two values in order to get this value for 1.18 L prime divided by B prime. I hope it's clear. The equations are here. The only thing is that you need to do those calculations for a few minutes. The reason behind that is that 0.5 H prime and B prime is given here, and H prime B prime 1.0 is given, but in our example we were given with 0.7. Therefore we need to linearly interpolate a value which is occurring somewhere in between here, which is 1.18 L prime divided by B prime. And if you calculate, you will come up with a value which is close to 0.128. Okay, so that was the modulus theory of elasticity and how we can find out the immediate settlement using the theory of elasticity. There is another method to calculate and to estimate the immediate settlement, and that is using the standard penetration test. And in standard penetration test, you might remember that we are given with a tripod, we are also given with a rope, hammers of 63.5 kilograms. I guess this is the weight of the hammer. A guiding rod just to guide the penetration of the rods, or the boring rod which is bored into the soil. Anvil is also placed, and the height, I guess it is around about 30 inches somewhere. And also we need to note down different intervals. We need to apply we need to we need to apply blows, and we need to record those number of blows. But for the first interval, I would call that as the first interval, and that interval is of 6 inches. Okay. And for the second interval, that is also of 6 inches. For the third interval, that is also of the 6 inches. Now the first interval is known as the seating drive. In order to avoid the disturbance in the superficial layers in the ground, we usually ignore the blows which are recorded in the first interval of the 6 inches, and we do record the number of blows which are taken by the soil in these two intervals, and that is known as the SPT and value. Information is given, the details are given about the external diameter, internal diameter, and the length of the rods, or the boring rods, are also given. We use split spoon sampler to collect the samples once we get the SPTN value, or if we are interested to collect samples from the desired depth of the foundation. So we use the split spoon sampler there. Weight of the hammer is also given. Height of the file is 760 millimeter or 30 inches. And the sampler is advanced under the impact of the hammer into 3 consecutive 6-inch increments. That has been discussed. Now the concept of the refusal has been discussed in here, that we need to count the number of blows, but if a total of 50 blows have been applied during any of the 3 6-inch increments, it means that we are hitting the bedrock there and a very hard stratum is there, so we need to stop at that particular point, and we will refuse. We will terminate the test. Okay. And a total of 100 blows if we are counting for 3 consecutive intervals. So if we reach 200 blows at that particular point, we will also terminate and stop the test. And there is observed advancement. If there is no observed advancement of the sampler during the application of 10 successive blows, for example, if you are applying 1 time, 2nd time, 3rd time, if the number of blows are 10 and there is no advancement of the rod appreciably, then we need to stop there as well. We already know that we need to advance it to 16-inch, and we will consider that first 6-inch as the seating drive, and for the second and third 6-inch penetration, we will count those 2 6-inch intervals, and the number of blows required for those 2 intervals will be recorded as the SPT and value. Now, split spoon samplers are used. As you can see here, this is usually considered as the undisturbed. This is the disturbed sample which is collected, and the reason for the disturbed sample is that we can clearly see that the thickness of those split spoon samplers are greater. Due to that, those samples would be significantly disturbed ones. Now, you cannot perform highly advanced tests, for example, direct shear test or the triaxial test or resonant column test or the local strain test or the bender element test on these samples. The reason behind that is it's significantly disturbed, but you can measure the moisture content, or you can perform the grain size distribution test on these types of samplers or the samples. How we determine that the sample which is obtained using the split spoon sampler is disturbed one, researchers have proposed this equation that if we compare the outer diameter and inner diameter, and if we use this equation, we will come up with the area ratio. And if the area ratio is greater than 10%, then it would be disturbed one. So greater than 10%, if the AR ratio percentage is 10%, and this one is here, for example, if it's greater than 10%, then it would be the sample which is collected would be the disturbed one, okay? And if it is equal to or less than, this will give us the undisturbed sample. For area ratio percentage which is less than 10%, it will give us the undisturbed samples. You can also do the calculation for the standard split spoon sampler, and you can clearly see that the area ratio is significantly greater than 10%. Therefore, we are going to get the disturbed samples. However, if we see here, if we use shell-bite tubes, and these shell-bite tubes are used in soft clays in order to collect samples in these types of clays, and you can clearly see the diameter, the outside diameter and the inside diameter, and the thickness is very small compared to the standard split spoon sampler. And if you compare the area ratio with the standard one, so it is much close to 10%. So we would say that if you are going to use the shell-bite tubes, this will give us the undisturbed samples. There are different types of hammers which are used. So if you see here, this one, this was the hammer which is uplifted using this rope, and then it is applying that blow onto the anvil, and that rod is going into the soil, and it's going to record the N value, and then we connect those sampler there and we collect those samples. So that's how it is happening. But there are different types of hammers which are used to apply those blows in different countries. For example, there are pin weight hammer. They were the earlier style. Then there is a safety hammer which is also used. This is the weight of the hammer which is applied, 63.5 kilogram. And this is the donut hammer which is used in most of the countries, in Pakistan as well, that there is a guiding rod and the hammer is uplifted and then it is released to hit this anvil there, and here is the drill rod. So this is known as the donut hammer. There is an interesting and important concept. If you see in here that the standard penetration test hammer efficiency. So based upon the different types of SPT mechanism and equipments there would be different types of hammers which would be used. Now the efficiency of those setup would be different, and we need to account for that as well. For example, if we are given with the theoretical input energy, which we can simply calculate using this equation, and if we compare with the hammer energy which is transmitted to the sampler, so there will definitely be losses in the theoretical and actual hammer efficiency, and we need to account for that, and we can use a table there for that correction. There is another concept particularly important when we are going to discuss with the correlations. Now you will see that we will find out the n value, and then we will go for the N60, which is the hammer efficiency correction. Then we will go for the overburden correction, okay? And then we will also see the different terms like N70, N55, and that is the correction for 55% hammer efficiency. This is the correction for 70% hammer efficiency corrections, and you will see those terms in different books and different literature. The reason behind that is that the hammer efficiency was different in North America, in Japan, in Far East Asia, so they were using different types of hammer efficiencies, and they have provided correlations, and the correlations means that if we get the n value or in 60 value or in 160 value or n70 value or n170 value, then we will get the soil parameters. So different correlations are available, and therefore we will see these terms in different tables in the coming few slides. But we can simply use this equation to find out the desired or the required N70 value. In this case, for example, we are given with the hammer efficiency of 60% and N60 value is given, which is 12. Now the hammer efficiency of the second equipment is 70%, which might be used in USA, for example. Now we need to find out the N70 value based upon this information, okay? Now how we can find out? We can find out this using this equation, which is eta h2 and 70 is equal to eta h1 and 60, or we can simply write that N70 would be equal to the N60 value multiplied by 60%, which is the hammer efficiency, by 70, and then we will get the corrected value for N70 or the 70% efficiency N value. Okay, now in this case you can take that value as 10.2 equal to 10. Okay, instead of 11 you can take 10. Please confirm that you can hear me.
Yes, sir, we can hear you.
Okay, thank you. Now we discussed about the n value. Now we are going to discuss about the N60, and we can also relate N70 as well. Now we discussed about the hammer efficiency, but there are other corrections which needs to be applied to that n value. For example, this is the hammer efficiency correction. Eta B is the borehole correction. Eta S is the sampler correction. This is the rod length correction and the energy correction as well. So once we divide that n value and we apply all these corrections, we will get the N60, which is the corrected, I would say, n value for field conditions. So we are trying to correct this value based upon, and the reason behind doing this correction was that, you know, in different parts of the country people were using different rod lengths, different samplers, different borehole diameters. So they wanted to come up with a standard value so that they can compare and they can get the different parameters, soil parameters. Now you don't need to worry about all those corrections there, because different tables are given for the hammer efficiency correction, or the borehole and the sampler and the rod length. For example, if you are using the different types of mechanism like the donut hammer or the safety hammer, which is used predominantly in North America, US, and in Japan they're using donut hammer. Argentina and China, they're using donut. In Pakistan, donut hammers are used, which is rope and pulley mechanism there. So the hammer efficiency is given here. So if in a problem it's given that, you know, we are using the donut hammer and the free fall, so the hammer efficiency would be 78%. And for the United States, for example, safety hammer is used, and the rope and pulley mechanism, it would be 60% efficiency. In our course we will be focusing on the 60% hammer efficiency there. Now for the borehole diameter, for example, if it's in the range of 60 to 120 millimeter, then you don't need to apply any correction. But if you are increasing the borehole diameter, then you might be using different types of corrections which needs to be applied to that n value. Now standard samplers are used, then no need to apply any correction. One would be okay. But if you are using for dense sands and clays, liners are used. Different types of liners are used to collect those samples in sands, because it's difficult to collect and get the sand samples. And in loose sands, if the liners are used, then you will use 0.9 that correction. Okay, a variation of the rod length, and if you're using greater than 10 meter, so no need to apply any correction there. If you are going to use, for example, 5 meter rod length, so you need to multiply that n value with 0.85. So this is the rod length correction, this is the borehole correction, this is the sampler correction, okay, and the hammer efficiency correction is given in these tables. Either you will be provided with these values, or the tables will be given in your quiz assignments or paper. Now, in cohesionless soils, as we discussed in Geotech 1 and Geotech 2, that at particular depth, like Z1, and here it's Z2. So if you remember, it's gamma into Z, and here it's gamma into Z. So if we are talking about the effective stresses, or if we say this is sigma naught, so that overburden will also increase the n value. So the n value which is recorded here, or which is recorded here, or which is recorded at different depths below the ground surface, it would also change, or the effect, in order to account the effect of the overburden pressure on the n value. So we can use this equation. Please kindly note down this equation as well, which is N160. So the incorporation of that 1 in the 60 and 60 term there, or symbol there, that means that the overburden correction has been applied, that 1, okay. So N160 is the value of N60 corrected to a standard value of sigma prime naught, which is 100 kilopascal. So you will use the Cn factor here. So you can use this one if you are solving problem in kilopascal or SI unit. If you are using foot-pound second system, so you can use this equation to find out the corrected N160 value. Now, as I discussed earlier on, that you might be confused when N value, N60 value, N160 value, okay, N70 value. The reason behind that is here, which is explained that in the literature, you will see that people, the researchers, they have provided different correlations with soil properties. For example, in this case, the relative density information is given in this table by a researcher, and he is relating the N160 value with the different types of sands or the cohesionless soils, or the relative densities are given. For example, if the N160 value is 7, so you can easily estimate that the relative density would be in between 5 to 30. If the standard penetration number, which is N160, or the corrected standard penetration number is 50, so we would say that it's a very dense sand and the relative density is 95%. There are other relations, and the correlations are also given. So if you want to find out the friction angle, so you can use this correlation, and that correlation is using N160 here. And if that value from the standard penetration test is given, so you can easily find out the effective friction angle. Now, looking at this table, so you can clearly see here that this table is using N170 corrected value, and if you want to find out the N70 from the N60, so we already discussed that we simply need to multiply that by 60 divided by 70, which is the 60% efficiency and the 70% energy correction. Now, for example, if we find out the N170, and the N170 is, for example, lies in this range, it means that this soil will be having a relative density of 35% or 0.35. It would be a medium dense sand. The friction angle of this medium dense sand will lie somewhere in between 32 and 36, and the unit weight would lie in between 17 to 20 kilonewton per cubic meter range. So that's how you can use different types of N values depending upon the different types of corrections which you apply. We can also find out the consistency, for example, whether it's very soft clay, soft to medium clay, stiff clay, very stiff clay, or hard clay, depending upon the N60 value which is given in this particular table. We can also estimate the consistency index. We can also estimate the unconfined compressive strength in foot-pound system and also the SI system. Now, if you want to use the undrained shear strength using a simple equation or a correlation using the N60 value, you can use the Hara et al. 1971 correlation. Now, back to the settlement or the immediate settlement correlation. If you remember, we started our discussion with the estimating the immediate settlement, and for the immediate settlement we need to find out the modulus of elasticity. So if you see here, different correlations are given here as well. In this particular column from standard penetration test, so you can clearly see in here that these correlations are used to find out the modulus of elasticity, or E, to estimate and to find out the immediate settlement. Cone penetration test data is also shared in this table, but as you already know that the cone penetration test data and the test would be discussed in your postgraduate courses. For the time being, we would be only focusing on the standard penetration test during the undergraduate course. Now, how we can estimate the immediate settlement using the standard penetration test? We discussed about the theory of elasticity, but now we will discuss the standard penetration test method. Please kindly note down this equation. Now QA is the Q allowable, N60 is the N60 corrected N60 value, which we obtained from the SPT-N value. F1 and F2, you can note down that F1 would be 0.0, I would say this one would be meter, and this one would be feet. So it would be 0.05 meter, and F1 is used in here, F4 is used here, which is 1.2 meter. This is equal to 4 feet. Now, if the width of the foundation B is less than or equal to 1.2, and why I'm saying this is 1.2, because that is equal to F4 in this table. Now, how about the delta HI? Delta HI would be the value of interest or the settlement value which we want to find out. For example, if I assume that we want to find out for 40 millimeter settlement, what is delta H naught? Delta H naught is equal to 25 millimeter. The standard value are equal to 1 inch. So this value will change, delta HI will change based upon the question which we ask in exam quiz or in assignment there, or even in the field. So based upon that N60 data, we can estimate the settlement. What if that the Q allowable, we need to find out if B is greater than F4, which means that the value of the width of the foundation is greater than 1.2. So in that case, we need to find out this equation. Please kindly note down this equation as well, because we are going to use this equation in solving the problem in a few minutes. Okay, now KD value, here is the value, which is dependent upon the depth of the foundation and the width of the foundation. You need to use this equation, and in order to use this equation, please confirm that you can hear me and the screen is visible.
Yes, sir, we can hear you.
Okay, thank you. Now, if KD value is equal to, for example, 1.5, so what should be the value of KD in the equation? What value we need to use? अगर हमारे पास KD की वैल्यू 1.5 आती है, तो बेस्ड अपॉन द मेयरहोफ 1965 रिकमेंडेशन एंड सजेशन हमारे पास KD की वैल्यू क्या होगी?
1.33 सर।
अच्छा, मोहम्मद अनस कह रहे हैं कि 1.33, बाकी लोग क्या कह रहे हैं, वो एग्री कर रहे हैं, वी विल यूज 1.33. Okay, good. So you understand what's in here. Now, this is a simple problem which you can easily solve taking the n average, and you can divide that is equal to 9, and you will come up with the n average value, and that n average you can get. Once you get the n average value, we need to find out the settlement, the immediate settlement which would be occurring in here. Now, assuming that it is n60, or the n average value is 7, and the depth of the foundation is given as 1.6 meter, which is from 1 to 4 meter depth, we need to find out the allowable bearing capacity for a 40 millimeter settlement, and we need to present that data as a curve for Q allowable versus B. So if you use the KD equation, so if you see here, the KD value should be less than or equal to 1.33. Now we can clearly see that this is greater, so we need to use 1.33 KD value. Now for the case, and now how we find out the KD value, because the depth value was given, but we started our calculation with the assumption of B value, which is equal to 1.5 meter. Okay, we need to find out the allowable bearing capacity, which will give us 40 millimeter settlement. For example, this should be 40 millimeter. Okay, we need to find out the bearing capacity here. Okay, now which equation we need to use, because we were given with two equations here. Equation number 1 and equation number 2. So if B is equal to 1.5 meter, for starting with the first assumption here, so as you can clearly see, B is greater than 1.2 meter. Now we need to use the second equation, because B is greater than F4 from that table. We will calculate and we will find out that it's 268 kilopascal. Then we will do calculation for B equal to 2 meter, and we will come up with 234 kilopascal. Okay, as B is greater than 1.2 meter or F4, therefore we are going to use the second equation, and we will create a table for the width of the foundation and the allowable bearing capacity. Okay, so if we do few trials, we can clearly plot that in Excel as well. So y-axis would be the Q allowable, and B, which is the width of the foundation. So we will plot this in a curve, which was also requested or desired in the problem. And now we can clearly see that we can see a trend that with increasing B, the allowable bearing capacity is decreasing. Why? Why the allowable bearing capacity is decreasing? with the increase in the width of the foundation? How is it possible? हमने तो अभी तक ये समझा है और पढ़ा है कि अगर हमारे पास विड्थ ऑफ द फाउंडेशन ज्यादा होगी तो हमारे पास बेयरिंग कैपेसिटी ज्यादा होगी। अब हम कैसे कह रहे हैं यहाँ पे कि अगर हमारे पास बेयरिंग कैपेसिटी कम होती जाएगी अगर हमारे पास विड्थ ऑफ द फाउंडेशन ज्यादा होता जाएगा? इसके पीछे कॉन्सेप्ट क्या है?
सर अगर विड्थ ज्यादा होती जाएगी तो इतना ज्यादा आबादी भी ज्यादा उस पर आएगा सर, तो बेयरिंग कैपेसिटी कम हो जाएगी सर।
फवाद, अनस, विसाम, हजरत बिलाल, हमजा, रीजन क्या है? वसीम कह रहे हैं कि अगर आबादी ज्यादा होती जाएगी तो उसके साथ हमारे पास अलाउबल बेयरिंग कैपेसिटी भी कम होती जाएगी। Anyone wants to add? अच्छा, तो यहाँ पे हम इसको डिस्कस करते हैं। So in here you can clearly see that we are now focusing on the 40 millimeter settlement. Now if we want to draw this curve which is based upon the bearing capacity curve for the shear failure criteria, this is for the settlement failure criteria. This curve is for the settlement failure criterion, okay? And this line or the curve will be based upon the shear failure criterion. Definitely, based upon the shear failure criterion, you can see that this bearing capacity is increasing. But in case of the settlement criteria, you can clearly see that when the width of the footing was 1.5, this 268 kilopascal will cause how much settlement? How much settlement would be caused by 268 kilopascal onto the 1.5 meter width of the foundation?
40 millimeter.
40 millimeter. Now if we are going for example 10 meter width of the foundation, and on that 10 meter foundation is 165 kilopascal of Q naught is applied. So how much would be the settlement here?
40.
40 mm, okay, 40 mm would be also here. So with greater width of the foundation, lesser Q naught is required to reach to that 40 millimeter. And for the case of lesser, the smaller value of the width of the foundation, greater Q naught is required, and that is because 2B is equal to approximately or we can say and 2b for this case would be significantly lower compared to this one. So different types of layers are required. Now if you want to draw a design curve in here, okay, if you want to draw a design curve, this one would be the lower bound design curve having the settlement and also the shear failure criteria. Now, if the width of the foundation is less than, for example, 2.8 meter, which design criteria should govern?
Shear failure, sir.
Shear failure criteria will be governing criteria. The reason behind that is because the Q allowable here is less at this particular point. If we are taking this one is greater and this one is the lower one, so the minimum of these two Q allowable, we will take that and the shear failure criteria is governing. However, if we are going from this intersection point where these curves are intersecting, so beyond that intersection point, the Q allowable here is less than the Q allowable here, which is obtained from the shear failure criteria. So the settlement criteria is governing from this point onwards. Now, this is a short problem which you can solve it. Only thing which is given here is Q is given in kilograms and N60 is given. You can use those KD equation and Q allowable equation. And if you see in here, 1.24, which is less than or equal to, I would say less than 1.3. So that's why you can use this KD equation. And delta HI is 25 millimeter. So H naught is also 25 millimeter. So you can convert that kilograms into kilonewtons. You can assume B value and you can come up with the allowable load as well. And you can come up with the B value to take 1000 of the kilonewton. Okay, so you can assume different values of B, and then you can see in here that how much load is applied. And once you see in here that 2.33 millimeter can easily take 126 kilonewton, and the applied load was 1000 kilonewton, so you can easily calculate you can estimate and you can find out the width of the foundation. There is also an equation, the problem example is given here that the raft foundation is placed at this level. The ultimate the undrained shear strength is given, which is the 300 kilopascal. Okay, Q ultimate is given, which is the average 300 kilopascal, and unit weight is given. N70 average is given for this particular layer, N70 is given for this layer, and N70 is also given for this layer as well. Now we need to find out the allowable bearing capacity, Q allowable, but now we need to satisfy both those criterias. For example, the factor of safety for 3 against the shear failure, and the settlement should not exceed beyond the 50 millimeter or equal to 50, sorry, millimeter, that is millimeter here. Now the shear failure criteria, we can use the Terzaghi's equations and Merhoff bearing capacity factors. We can find out easily the Q SAF, which is 334 kilonewton per square meter. And we can find out the 334 kilopascal here. Now if we want to find out the modulus of elasticities, so you can use different correlations, and the correlations are used in here. You can clearly see those correlations which were given in this table as well, in the lengthy table, to find out the E values or the modulus of elasticity values here. Okay, so these values are given here. So just find out those E values, and once you find out you can take the weighted average. You can assume B prime, H prime, and B prime. You can use the mu value, and after interpolation, you can find the I value, and using this equation, you can find out the Q naught, and you can clearly see that the settlement criteria is governing, because the shear failure criteria were giving us 334 kilopascal, and the settlement criteria is giving us 204 kilopascal. So in this case, settlement criteria, and in most cases, settlement criteria governs, and that's how the Q allowable and the width of the foundation changes. Thank you very much for listening very patiently. Now we will move towards the question and answer session.